Okay, so here's what we were talking about last time. So we were, let me rewind a little further. So here's sort of the big picture strategy of what we're trying to do. We're trying to take advantage of a structure of ideas that we saw with the fundamental theorem of line integrals. And we kind of want to ask the semi-outrageous question, can we do kind of that sort of thing but two-dimensionally? Right? So let me remind you what the fundamental theorem of line integrals, the big idea is that we have this accumulating quantity that we compute on the boundary, right? But it accumulates over the interior. So the quantities change. And how much does the function change from, this one side of the boundary to the other side? And specifically, realizing that actually accumulates over the interior, right? So that was the first point of view that I'm taking on the fundamental theorem of line integrals. Likewise, fundamental theorem of calculus, same. Again, this is sort of our second rip-off. We've already ripped off from the fundamental theorem of calculus. And then, secondly, that there is an associated notion of density. If you think of change, algebraic though it is, right? It's an algebraic quantity. It's a formula. But if you think of it as a kind of, it's accumulating like stuff does. Maybe it's a kind of a stuff. It behaves kind of like mass. It accumulates like mass. Maybe it has other things in common with mass. So, along those lines, is there an associated notion of density? Is there a notion of change density? Absolutely, right? That's what the integrand is in our eventual integral in the fundamental theorem of calculus. Change per unit size. Now, of course, in the fundamental theorem of calculus, change per unit size, we tend to think of that as slope, right? Because we're so accustomed to thinking about single variable functions as graphs. And again, I want to let go of that crutch. Try to think about the fundamental theorem of calculus differently. But nevertheless, along those very similar lines, we have this idea of a density, and can we extend that to a two-dimensional setting as well? So back to where we were. Do we have an accumulating quantity in the form of our new object of interest here? Let's see, I want to color code green. Boundary circulation. Right, that's our new quantity of interest. Does it accumulate? Now, this time we're asking, does it accumulate over area? Right? So given that I have a total area, I can talk about its boundary circulation. Keep in mind, boundary circulation is oriented. It goes in a certain direction. Is the boundary circulation for the whole, is that the sum of the boundary circulation individually for the two parts? So here's the boundary circulation for the left part of that area, and now looking at the right part, this right piece of area, the boundary circulation there, like that. Right? These are the three circulations we'd have to look at if we want to ask, does boundary circulation accumulate? Is the boundary circulation on the whole the sum of the boundary circulations on the two parts of area? I need for orange plus blue to equal to purple. And at a glance, it doesn't look like it does, because look, there's all this stuff happening over here on this new line segment that is not part of the purple boundary circulation, right? But then we make this observation that we did last time. This is just a reminder. That looking at these two pieces, we're going that way when we're doing the blue circulation. We are instead going this way when we're doing the orange circulation. So there's two new pieces of line integral, and they cancel just perfectly. Right? And so it's like they're not even there at all. So now let me redraw the picture. Let's do this with a pencil. Here is the purple circulation. All right. Then we have that blue circulation, and we have this orange circulation. And the cancellation of these two pieces, the fact that these cancel, is what makes it, even though at a glance it doesn't look like it, those canceling is what makes it, in fact, highly satisfying, and furthermore true, that blue plus orange is indeed purple. Okay, all right, so that's how that works. Now, I wrote this down algebraically. We didn't talk through the algebraic version of this last time. This is just algebra. But it's nice to sort of make the connections. If I want to write the pieces of line integral that I was just talking about, so for example, this one here, if I want to write that, sorry, I can't, I'm having drawing incompetence issues. If I want to write the line integral over that curve, specifically in that direction, right? If I want to write that algebraically, I got to give the curve a name. If I'm going to write an integral with a name for the domain, that piece of domain has to have an orientation to it. So I'm going to label C1 as this piece of curve oriented in that direction. It's an arbitrary choice, but I'm just going to choose to define C1 to be that way. It doesn't really ultimately matter. And so that blue circulation I can just write as integral over C1. C3, I'm defining, let's see here, I better make a better colored choice. C3, I'm going to define to be this piece of curve. Again, I've got to give it an orientation if I'm going to give it a name. I'm going to define it oriented that way. Again, arbitrary choice, no particular reason. And having made that choice, that second piece of circulation around the left side is integral over C3. Now, having made those choices, though, notice that on the other side, looking at on this side over here, my boundary circulation, recall, is, well, it's that, which I can call that C2, and I can say, okay, there you go, right? But then plus, awkwardly, that. Now, problem, I've already named C3, I've already labeled oriented C3 as oriented upward. So if I want to talk about this this piece of, part of the boundary of C2, if I want to talk about that piece of circulation, that piece of line integral, how does this relate to a line integral along C3? Well, it's going the wrong direction, so it's the minus, right? Because it's going the wrong direction, I get negative of the line integral on C3. And so you look at how these add up, and again, just like we talked about geometrically, these two pieces cancel because they are opposites of each other. So this is just an algebraic version of what we talked about geometrically a couple seconds ago. For your consideration. Okay, so nice punchline then. As we were hoping, the circulation on the union is, as expected, the sum of the circulations on the pieces. In other words, boundary circulation does accumulate. And now, let me recognize a legitimate gripe. Yeah, you only cut this thing into two pieces. What happens if you cut it into more pieces? Beautifully, exactly the same thing. So, here we go. In fact, here's the equation we'll have eventually. So let's suppose we have a solid two-dimensional region, and we dice it dramatically like we do there. Okay, right? Well, the boundary circulation around the boundary of the whole thing is that the sum of the individual circulations around individual pieces. So here's a little piece, di. For example, let's look around the boundary of di. Here, I guess I'll circle. Looking around the boundary of di, well, there's the circulation around the boundary of di. If I then add up over all of these pieces, right, adding up over all of those pieces, I'm going to be adding up a bunch of circulations, well, that all kind of look the same. Now, again, always counterclockwise. It takes a second to fill in a few of these for sort of demo purposes. There's a bunch of these boundary circulations going counterclockwise. And notice on this shared edge right there, we've got two line integrals going opposite directions, and therefore they cancel. Right? Familiar? On this shared edge, we've got two little line integrals going opposite directions, and therefore they cancel. On this shared edge, two line integrals, opposite directions, therefore they cancel. Notice the pattern. This just keeps happening. What do you think is going to happen on this edge? Right? Well, you're going to be going around that edge counterclockwise in both cases, but which punchline means you're going opposite directions, and therefore on that edge, those two terms cancel. So all of the interior edges cancel, and just as we predicted, all that's left is the boundary pieces, which add up to exactly what they're supposed to. So, yeah. Mm-hmm.
Could you explain which way we circulate again?
Yeah, always counterclockwise. If you're talking about around the outside boundary, always counterclockwise. So that's a convention of what we mean by the word boundary, right? So if we just decree that when we go around, and let's just say an outside boundary, so we don't have to worry about the little interior pieces. We decree that whenever we go around an outside boundary, we always mean counterclockwise. So when we say boundary circulation, we always mean, promise now, always mean counterclockwise boundary circulation. Right? So that's the quantity of interest, and it's because we make that promise that we get this nice punchline that everything cancels. Yeah.
Thanks.
Yeah. Okay, so this, again, is how it looks when you write it down algebraically, and let's see here. So boundary circulation is the sum of little pieces of boundary circulation. By the way, let me recognize real quick for the moment, isn't that a scary looking equation? At a glance, not thinking about what the pieces are saying, I think that's scary looking. Right? So what I want to warn you all about and try to encourage you is, if you see something scary looking like that, just take a pause, right? Take a nice deep breath. Look at one little piece at a time of the equation, and then think about how those pieces relate to each other. And this scary-looking equation, scary though it is just saying, as we've already discussed, that the outside circulation and these inside circulations relate in that if you add up all of these inside circulations, you get just the outside. In other words, really what this is saying is that those interior pieces cancel. Ultimately, what this is saying is that these two line integrals cancel. Right? So, scary to look at, but it's really making a kind of a statement about the geometry of how this all works out. Okay. All right. So, as we've done before, something that's always the same, you can take a limit as n goes to infinity, and it's constant, so take the limit all you want. It doesn't make any difference. Then we notice that, golly, this looks a lot like a double integral. We are, in fact, adding up over the entire interior there. And starting to look like we might have a double integral showing up here. Okay. All right, but let's not get ahead of ourselves. If this is going to be a double integral, I need area over there. I don't have an area over on the right. Sound familiar, right? I mean, so this is we made an analogous argument when we were talking about the fundamental theorem of calculus. Hey, we need a delta x over there. So here we need a delta a. So okay, let's think about whether we can do that. Can I multiply and divide by delta a, thus giving me the delta a that I need? Is what the integrand thus turns into actually a thing? Is this something? Is it something I recognize? And if not, is it at least something that I can compute? So to the first question, is this something that I recognize? Is it like the derivative or something? No. That's where the analogy breaks down. It's not something we recognize. And a little bit of a disappointment, but this nevertheless is something that I can totally compute. And that's some details. It's not that hard of details. It's just I feel like it's a distraction from what I think is really the big point of what's going on here. So I'm not going to show you those calculations. But this thing is perfectly computable. And what it is in the limit is this formula. And now, having seen this formula, now you might recognize it. That's Green's operator. Okay. Now, reminder though, what does therefore this represent? Well, what this means is, and let's write this whole thing down before I go back and not get ahead of myself. Circulation accumulates. Right, this is the first thing we talked about today. Multiply and divide by area, because that's perfectly legal. Thus, finding ourselves happily now with a double integral, but with a mystery of what is this integrand going to turn into? Well, we on the previous page, I claimed that it turns into this. And notice that we have then a new equation. This is called Green's theorem, by the way, and I'll talk about different versions of it in a second. But this is Green's theorem. And if we ask then, what does this represent? It's a density. It's a different kind of a density. Let me just walk you through sort of the ideas here of how this is a density. This is an accumulating quantity. This thing over here is accumulating over the area. It accumulates just like mass would accumulate on an area. Right? It's got that same sort of algebraic feature that mass does. It's like it's a stuff. Let's treat it as if it's a stuff. So this accumulating quantity is how much of the accumulating stuff you get per unit area. It's stuff per unit area. It's a density. It's very natural to view it as a density. Okay. So that's, again, the way I want you all to think of this. I want you to think of this as a density, because it is. Here, let me highlight. It's a density because we're talking about stuff per unit size. That makes it a density. What kind of a density? Is it mass density? No, it's not mass. It's not mass per unit area. It's circulation per unit area. So in the same sense that mass per unit area is mass density, well, this is circulation per unit area. This is circulation density. Right, now, I personally feel that this is a highly undersold point of view on Green's operator. The easy point of view that you can take on Green's operator is it's this formula, and it's the integrand in Green's theorem. And that's nice and all, right? But what does it look like? How should I think about it? And what intuition can I have for what this formula really represents? I think that's best understood as calling it circulation density. Okay, I'm a big believer in analogies, right? Remember when we were talking about fundamental theorem of calculus, I pushed this seemingly weird, probably actually weird point of view that the derivative, you can think of the derivative as being a density, right? It's change per unit size, and it's also rise over the run, which is a slope, and I know that's the comfortable point of view, but it's also a accumulating quantity per unit size in the domain, and that makes it a density. The more comfortable that you get with that point of view, the more you dwell on, think about, digest this idea of thinking of the derivative as being change density, the easier it will be for you to get some sense out of Green's operator and understanding Green's operator analogously as circulation density. Okay, so I want to push that point of view. I'm a big believer for your consideration. Okay, so that said, here's the formula that we just derived, and I recopied, kind of recopied it. I'm going to say there it is. Right, same thing. And now let me just show you that there are different ways that you can think about this. We've already talked about some of these. There's this kind of awkward point of view on vector line integrals, right, what I call coordinate line integrals, right? A vector line integral is made up out of individual coordinate line integrals. It's an awkward point of view notationally. It has its merits. But if you observe that those are the same, then here's an alternative form of Green's theorem. This is how it gets written down in a lot of books, a lot of places. It has the nice feature that, the thing that is the P, that goes there. And, this thing here, okay, well, that goes there. So you can see the immediate connection between the left side and the right side. And that's nice, I suppose. Also, just, don't forget again the big point of view that I've been pushing on, what is this thing that we're computing? You can think of it as counterclockwise boundary line integral, right? That's algebraically, what it is. But circulation, I think, is a very natural point of view as well. And, I've written there boundary circulation. Well, if you think about it, it's sort of implied. Right? Circulation means you're looking at how the vector field goes around a closed curve. Well, that is a boundary. Right? So you could just think of this as circulation. I like to go ahead and put the word boundary in here just as a kind of a reminder. Don't forget, of course, we're talking about circulation around the boundary, right? But it's sort of superfluous. Okay. And again, along those same lines, don't forget we just argued Green's operator, aka this formula. I mean, the way to think about this is circulation per unit area. So circulation density. So there's another, I think, really important point of view on Green's theorem, is that there's an accumulating quantity, and it's therefore an integral of an associated density. Stuff accumulates and stuff has density. I mean, it's really kind of what this is saying. And that's, again, I think really, really important. Again, just for analogy purposes, along the lines of mass being a double integral of mass density, right? Structurally the same kind of equation. Okay. All right. Okay. So let's see an example. Oh, you know what? Before I show you an example, let me come over here to our diagrams. Hope y'all remember these diagrams. It's kind of an organizational tool for keeping track of the things that we've talked about and how they relate to each other. We talked about how boundaries, if you take a two-dimensional region and look at its boundary, well, you get a curve. That's just geometric observation. If you take a curve and look at its boundary, well, you get a couple of points, right? And there are these kinds of evaluations that you can do of certain kinds of, noted here, integrands on those kinds of things. So notably, you can do an integral of a function on a two-dimensional region, right? But line integrals have an integrand that's a vector field, not a function. Okay, so these are the objects in play. By the way, we've also already noted that these operators fit together. They kind of Lego together, right? Because what comes out of the gradient operator is a vector field, but that's what goes in the Green's operator. So, again, when you see Legos, there's this urge to want to put them together, right? And that's kind of an option here. It turns out that other than that sort of fun instinct, there's also really natural reasons. And we've talked about how if you have a gradient, Green's operator will give you 0. Right? We've talked about how if you have a vector field for which Green's operator is 0, it is a gradient of something. Right? Regularity issues aside. Okay, so a lot of stuff that we've done here. Let me remind you, the last thing that we did with this diagram was to think about the sort of the pattern, the diagram chase of, what does the fundamental theorem of line integrals look like on this diagram? And we noticed that, well, if it's about when you take a curve, look at its boundary and evaluate on that boundary. And then likewise, if you apply the operator, the gradient operator, and do a line integral of that gradient on the original curve, you get the same thing. This is the fundamental theorem of line integrals can be thought of as, hey, this little diagram chase works out. And the wonderful thing is that Green's theorem is the same diagram chase. I mean, just for dramatic purposes, I like to just slide the diagram chase over like that there. Because to emphasize, it's the same pattern, but now let me draw it a little bit more aesthetically pleasing. If you have some region, if you have some two-dimensional region and you look at its boundary curve and do a line integral of some vector field on that boundary curve, so I like to abbreviate that like so. On the other hand, if you apply Green's operator to that vector field, and then do a double integral of Green's operator on your original domain, right, then you get the same thing. So I think that's really, what's the word I'm looking for? It's an eyebrow raiser. It's a little dramatic that these two very, very different theorems, one's about two-dimensional regions and their boundary curves and circulations and stuff. The other theorem's about gradient fields and endpoints of curves. Geometrically, they look totally different. Algebraically, they look pretty different. And yet structurally, in this pattern, that this diagram of pattern that we're noticing, they're really the same thing. Okay. All right. Okay. By the way, heads up, this is the pattern that we're going to be, mining this pattern a lot. I mean, it worked out with the fundamental theorem of calculus. Then it gave us the fundamental theorem of line integrals by copycatting. Now it's given us Green's theorem by a little bit more abstractly, but still structurally copycatting the same pattern, right? And then we're going to go into R3 pretty soon. And we already have a fundamental theorem of line integrals, but we're going to find ourselves with a couple more theorems. We're going to talk about something called Gauss's divergence theorem. It's the same thing. And Stokes's curl theorem, ultimately, it's the same thing, just in a different context. So again, those details to come later, but that's a little, I like to do foreshadowing. That's a little bit of foreshadowing of what's coming soon. Okay. All right. So here we were. Do this example here. We want to compute a line integral. Side note, we have a bunch of tools for computing line integrals. One of them is parameterize the curve, plug and chug. Perfectly respectable way to compute a line integral, no problem. Another way to compute a line integral, fundamental theorem of line integrals. Right? Seems like a natural choice given the name. Right? And that's another thing that in some cases you can do that. Right? But notice we now have a third choice. Again, going back to our diagram. If you want to compute a line integral, you can use Green's theorem and rewrite this as a double integral. Again, now stuff's got to line up. You've got to make sure that actually works, but very often you can. Okay, so that's what we're going to do here. Before I get into those details, let me point out, let's suppose you have a line integral and you want to use the fundamental theorem of line integrals. Sorry, my stylus. Suppose you want to use this theorem. You're computing a line integral. Does the fundamental theorem of line integrals always work? No. Very conspicuously not. Look, it says right there. This only works if you're talking about a vector field that is a gradient of something. Not all vector fields are. And many, from a certain point of view, most vector fields are not gradients. Right? Nevertheless, it's surprisingly, persistently common to happen in engineering and physics life. But anyway, it's certainly a condition. You got to check. You can't just apply the fundamental theorem of line integrals. You got to have an anti-gradient. Okay. So, it turns out there's an analogous concern over here. Can you use Green's theorem to compute a line integral? Well, again, not necessarily, and dramatically and very visibly, it says so right here. This is not just any old line integral. This is a line integral specifically around a boundary curve, right? Your curve has to be a boundary of something. You might say, depending on how much you like this little grammatical construction, you might say your curve has to have an anti-boundary. I don't know. Anybody like that? I think that's adorable. Anyway, you have to have a two-dimensional region whose boundary is your curve, because it says so right here. We're computing line integrals around boundaries. Okay. This is a common mistake that students make, to forget this condition, forget to check. And I think y'all probably know what I'm talking about when I say that, very often we'll write integrals without writing what the domain is. It's like, okay, well, yeah, whatever. I mean, that's understood or implicit, and we'll write, integral f dot dx or whatever, and then this is just like I'm just saving time, right? But it is a big deal here, and if you're sloppy about this, you don't think about what the domain is, and likewise on the ensuing double integral, if you're not thinking about what the domain is, I see this happen every year, every semester. Students will have a line integral and they'll say, oh, line integral. Okay, cool. Well, that's a double integral of Green's operator. No, not necessarily, right? I mean, it just does not work unless we're talking about a boundary, not for sort of technical, uptight mathematician reasons, but because we need that anti-boundary to exist, right? That is this domain here that I kind of conveniently omitted to note. If it doesn't exist, then there is no double integral at all. This is not a minor technical point. This is a huge point. So you could even see why. I mean, why is it important? Well, the curve, right? We turn this into a double integral by breaking up the interior, sort of slicing up the interior into little pieces and looking at their boundary pieces. So I'm going to need that interior. If your curve is instead this, what are you going to slice up? Not only does the theorem not work, you can't even start the argument, right? It's complete and utter meaningless nonsense to write down Green's theorem unless your domain for your line integral is a boundary of an actual two-dimensional region. Okay, so I got to make a big deal out of this because again, I think my practice of making a big deal out of this has reduced the number of students who make this catastrophic error. But again, it still happens sometimes, so I got to keep doing it. Okay. All right. So back to our example. All right. So our curve that we're interested in here is described there. The vector field is here. So again, you can plug and chug if you'd like, but let's use Green's theorem. First thing to observe, let's think about that curve again. It says right there it's a boundary. Specifically, it says it's the boundary of the unit disk, and it even emphasizes counterclockwise, right? So there's our curve. Is this a boundary? Well, again, yes, it's given right there. It's the boundary of the unit disk. So that's the anti-boundary. I really like that terminology. The anti-boundary is is that solid unit disk, and so this is in fact a Green's theorem question. Again, Green's theorem says I can only address line integrals that are around boundaries. This is indeed a boundary. Okay, so always got to check that first. That said, Green's theorem tells us that boundary circulations are computed with double integrals. And so we've got a double integral to compute here. Now, before I finish with the rest of the algebra, let me make another observation, and that is that Green's theorem doesn't have that satisfying punch that fundamental theorem of line integrals and fundamental theorem of calculus have, both of which you rewrite your line integral as f of b minus f of a, and at that point you just plug right on in there, and it is unavoidably simple to answer the question. Notice that didn't happen here, right? What I've done is I've turned an integral that might be hard to compute into another integral that still might be hard to compute. So another sort of unfortunate difference between those earlier theorems and Green's theorem. Green's theorem is not an automatic, good news. In fact, it could be that this double integral might be harder to compute than your original line integral. That happens. Okay, so think of Green's theorem as functionally kind of like, it's like the substitution rule in single variable calculus. If you use it well in situations that are susceptible to it, then it can make your life easier. But there's no law that says you just put in any substitution. There's a random substitution and your integral will necessarily get easier. Sometimes it gets worse. Right? So anyway, it's got that in common with that. In this case, and again, I rigged it up where this would work out nicely. Oh, come on, stylus. The x partial of that is 3. And the y partial of that is 1. And so qx minus py is easy. It's just 2. So this lucky break, again, I rigged it up this way. This turns into an easy double integral to compute. It's just 2 times the area. The area is obviously pi, and so. Okay. Let me pause for a moment for questions. I have another example coming up, and then a few applications. Everybody good? Okay. All right. One more example. So let's look at this line integral. Now this is a kind of a weird one. We're looking at a line integral. The curve is what I've got drawn here. It has what I'm going to call 4 pieces. Kind of a figure 8, sort of a triangular figure 8, if you will. That's my curve. Yeah. Oh yeah. Mm-hmm.
Sorry, I had a question. Mm-hmm. Is the bounds for the one above 0 to 2 pi, 0 to 1?
Those would be so 0 to 2 pi would be the bounds if I parameterize the curve, but I'm not parameterizing. So the bounds have to correspond to the differentials, right? So when you have a vector differential, there aren't really so much bounds as a domain, right? So the domain is dx. So sorry, the domain is the curve C. Sorry.
So would you evaluate the?
Yeah. So right. So this integral here, this is an area integral. The domain is this solid 2-dimensional region there. So in other words, it's a section 14.3 kind of a problem. 14. I think that's the right number. Yeah. Right. So now, if you were to say fooey on all this Green's theorem stuff, I'm going to take this thing and I'm going to parameterize it. Then you would have an integral of a bunch of stuff dt. And then these bounds, what would these bounds be? Well, it depends on your parameterization, but if you use sines and cosines, which would probably be an easy way to parameterize that curve, then yeah, it may probably 0 to 2 pi. But that's just not what we're doing, right? Because of, right. Okay. Okie dokie. So weird curve, right? Now, why would I want to do a line integral on this curve? I mean, look, maybe I'm driving across, a route for some reason, and I'm keeping track of something as I'm driving. And maybe I'm driving, look, you might drive along a path that crosses itself. It's not the weirdest thing in the world. Right? Okay. All right. So again, it's a line integral. So yes, you can parameterize and plug and chug. Let's not in this case, but you could. I'll point out that would be a bummer because you would have to parameterize that line, which algebraically would be different from the parameterization you would then have to do of this line, and then subsequently you'd have a third parameterization of that line. I mean, you'd have 4 separate integrals to compute if you parameterize and brute force it. So, right, that's undesirable. Let me address this question. Can I use the fundamental theorem of line integrals? Or let's even go back up here. Could I have used the fundamental theorem of line integrals on this one? And there's a temptation to say, hey, all I'd have to do is find the anti-gradient, fingers crossed, hope it exists. Right? And then f of b minus f of, it'd be a straight plug and chug, and that'd be nice. And I claim that if you try that, it will fail. Remember, not every vector field has an anti-gradient. This vector field does not have an anti-gradient. And in fact, the reason I know that this vector field does not have an anti-gradient is now on the page. If it had an anti-gradient, Green's operator would have to be 0, and oh, look at there, it's 2. 2 is not 0, therefore this does not have an anti-gradient. I think that's kind of an interesting observation. The thing that you compute to use Green's operator is to use Green's theorem, is also the thing that lets you know if you could have used the fundamental theorem of line integrals. And back to the diagram. Right? colors. The thing that you use in Green's theorem is the thing that you compute to let you know if you can use that theorem. It's Green's operator, both cases. Yeah, neat little sort of coincidence, or let's say it this way, example of how the diagram makes things simple. Okay. Right, so likewise in this next example, Green's operator, I'll sort of skip to the punchline. You can see it right there. There's Green's operator. It's not zero, so we can't use the fundamental theorem of line integrals. Okay, fine. Okay, so the big idea on this one is to try to figure out, is this curve a boundary, and if so, what is it a boundary of, and then apply Green's theorem. So it's tempting to say yes, that it's a boundary. Just keep in mind that that's a loaded term. At this point, the word boundary now means always. The word boundary means counterclockwise. Right? I'm going counterclockwise around D1, right? But I'm not going counterclockwise around D2. I'm going clockwise around D2. So tempting though it may be to say, hey, this is the boundary of D1 and D2, sort of the union, right? No, it's not. So what I can do, though, is say, well, look, I'm going around the boundary of D1, and as for the boundary of D2, well, yeah, I'm not going around the boundary of D2, but I am doing a line integral that is the exact negative of going around the boundary of D2. Because I'm going the exact wrong direction. That's another little cute observation that, wrong is not good, but exactly 100% diametrically perfectly wrong, that's the exact negative, right? So sometimes the more wrong you are, the more useful that information is. In some cases, I think that's a nice example of that. Okay, so these paths that I'm moving along, it's not really a boundary by itself, but it is the difference of two boundaries, you might say. And then each one of these you can apply Green's theorem. Don't forget the minus sign. The minus sign is important and it follows along, right? Individually, each one of these integrals is an area. That's just an integral of 1. So I'm looking at, here, let me do it like this. I'm looking at this area minus then this area. And those areas are obviously the same, and therefore this integral is 0. Yep?
If we didn't know the areas of whatever we're trying to integrate, what would we...
Yeah, then this is one of these deals where, Green's theorem is not a magic wand, right? It allows you to turn a question into a different question. And sometimes, fingers crossed, that new question is more convenient. And if it's not, then maybe Green's theorem is not that helpful. So there's no perfect answer to that. Yeah, right. Okay, how are we doing? Oh, gosh. Okay. I'm going to go real fast through these next 2 pages because it's a clever corollary, as I have it labeled here, but this is just an observation. I'm going to apply Green's theorem. There it is, by the way. There's Green's theorem. To a special case. Let's think about what happens if I consider the vector field 0, x. Well, that turns the integral on the line integral on the left into this, which of course you see that 0 there. It means it really turns it into that integral x dy. But also, this vector field, 0, x, that is an explicit vector field. I can compute Green's operator on it, dq dx minus dp dy. It's 1. And an integral of 1 gives you area. So, as applies to this special vector field, Green's theorem becomes what appears to be a new kind of a theorem. And this new theorem says, if you want to compute an area of something, right, that's a pretty reasonable question. Comes up sometimes. You want to compute an area? Well, coordinate line integral x dy is a line integral that computes this otherwise double integral. So this can be quite convenient. Something that makes it even more convenient is the special case if you're talking about a line segment. It turns out that this integral x dy is really easy to compute if you're talking about a line segment. You'll note here I'm going to leave this as an exercise for y'all to do. Y'all can totally do this. If you have a line segment between 2 points, you can parameterize that line segment. That's a chapter 12 problem, right? It's you'll recognize the form that we used in chapter 12 is it's like x naught plus tv, right? Or a plus tv. We used both of those. So just take that. You can directly parameterize that line segment. Having parameterized that line segment, you can plug and chug compute this integral. It's just a matter of doing it, right? And what you will end up with is, kind of shockingly, the average value of x on that line segment, namely the average of the endpoint, x coordinates, times the change in y across that line segment, namely y2 minus y1. And that's a neat little, good. And notice how easy this is to compute. That's arithmetic. Right? So beautifully what this turns into then is areas can be computed with a line integral, and line integrals can be computed with easy arithmetic, and therefore areas are going to be computed by easy arithmetic. Example, suppose you want to compute the area of this awkward, what is that, a 1, 2, 3, 4, 5, that's a pentagon, non-regular pentagon, non-convex, weirdo pentagon. How would you compute that area? Oh gosh, right? I mean, none of the angles are right angles, and it's just all lumpy and weird. How do you compute that area, right? So, neat fact, area is computed with that line integral. That line integral is the sum of 5 separate line integrals on individual line segments, each of which is easy to compute with the formula on the previous page, and a little arithmetic gives you your answer. And this area in here, that area is 17 halves, as it turns out. That's kind of neat. Okay. Everybody okay? Okay. All right, let's see here. I have a minute 15 left. You know what I'm going to do? I think I've gone over several times. Y'all all have observed that, I'm sure. So I think I probably owe you that minute 15. So let's draw the line right here for today, and we'll pick up here on Friday. See y'all later.